Hi everyone. In the last video, we spoke about these new units, the Unified Atomic Mass Unit and electron volts. And that video, together with the first one in this little series, which was about binding energy and specifically the binding energy per nucleon, will now lead us on to understanding nuclear fission and fusion. If you think back to 2 videos ago, we spoke about binding energy per nucleon, and we said that the binding energy per nucleon is what determines how stable an element is. The higher the binding energy per nucleon, the more stable it is. So what I have here is a graph where along the x-axis I've put the mass number of different nuclides, and on the y-axis we've got the binding energy per nucleon for that particular nuclide. Now let's see what happens. If you'll notice, hydrogen down here, that's hydrogen 2 actually, which has a special name, deuterium, but that down there, that's quite low down there, so that's got quite a low binding energy per nucleon. For the first few nuclides, as we climb and we get higher in our mass number, that is when these 2 nuclides are fusing together to form a new nuclide where the sum of the parts is greater than, the sum of the mass of the parts is greater than the mass of the whole. So for example, if you fuse 2 of these together to make a helium-4 nuclide, then the mass of that nuclide will be less than the mass of the 2 deuterium nuclides, and as a result, the binding energy per nucleon will be higher because you've got more energy to share amongst those 4 nucleons. So as you can see, as we go, we climb up. That means that helium-4 is a more stable nuclide than these ones below it. And we continue to climb. There's a couple of dips in there as we go to lithium and nitrogen-14, etc. But the general pattern is for these first few elements we are rising, and as the mass number increases, the binding energy per nucleon is increasing as well. Which means that as we are in this first part of the graph here, as our mass number increases, we follow this pattern where the more energy, the greater the mass number, the more mass gets converted into energy, therefore there's more binding energy and more binding energy per nucleon. In the next video, we're going to look at what happens in this second half of the graph here, but for now notice that the nuclide with the highest binding energy per nucleon is iron 56, that nuclide there, and that divides our graph in half. Today we're talking about nuclear fusion, when we have these smaller elements combining to create a larger one, and therefore we're only going to talk about the first half of this graph here. Since the binding energy per nucleon is increasing as we go as we increase our mass number in this first half of the graph, it means, as we said before, that more mass is being converted into energy as our nuclides are fusing together. That energy that is created, that extra energy, that the mass defect, if we remember from video 1, when the mass defect turns into energy, that process there, that energy that is created is also released and can be harnessed, for example, in nuclear power. So let's see how that would work with an example involving nuclear fusion. Okay, let's say that we have a nuclear equation where we have a hydrogen nuclide and a deuterium nuclide, so that's just the fancy name for hydrogen 2, and those 2 fuse together to form a helium-3 nuclide, like that. Let's see if we can calculate how much energy is released in this reaction, and I'm going to do it twice. First I'm going to do it using the new the new units that we developed in the last video, the atomic mass units and electron volts, and then we might do it again using the old SI units of joules and kilograms. So let's start. We would look at our table that would be, and remember, this would be, all of this information I'm about to write down now would be given to us in the question. You don't need to remember any of these numbers I'm about to write down. Hydrogen 1 has an atomic mass unit of 1.00783. Deuterium has an atomic mass of 2.01355, and helium-3 has an atomic mass of 3.01603. So what we need to do here is we need to calculate the mass defect. The mass defect. And the mass defect, this is exactly the same as the examples that I went through in the last couple of videos. The mass defect is going to be when these two smaller nuclides fuse together to form this larger one, some of that mass will be lost and turned into energy. Let's calculate how much of that mass is lost. So if we work out what is the sum of all the masses on the left-hand side of the equation. So on the left-hand side, we have 1.00783 plus 2.01355. I'll get my calculator. And that equals 3.02138. On the right-hand side, we have a mass of 3.01603. Notice, like we expected, the sum of the masses on the left is greater than the sum of the masses on the right. That means that my mass defect is going to be 3.02138 minus 3.01603, which equals 0.00535. That is the mass that is lost when these two nuclides fuse to form helium-3. We can then multiply the mass defect by 931, and we get that that would equate to an energy of 4.981, and let's round that to 4.98 mega electron volts. That is the energy that is released in this reaction. So when we're talking about nuclear fusion, that energy, which in the last couple of videos we referred to that as the binding energy, because it's the energy that is released when the two smaller nuclides fuse to form the larger one, some of that mass is lost and it's converted into binding energy used to hold this larger nuclide together now. But we can also now think of that energy as the energy released in the reaction. So in future videos, when we start talking about nuclear reactors and nuclear bombs and other ways that nuclear energy is used, that is where this energy is coming from. It's the mass defect being converted into energy. I said I was going to do this example using the old SI units as well, but I might leave that for another video. This is an example of nuclear fusion. As we're climbing in this first half of the graph up to iron 56, anything to the left of that, as the two smaller nuclides are fusing together to form a larger one, some of that energy is being lost. It's being converted into binding energy, and we can also think of that energy as the energy being released in that reaction when those two smaller nuclides form together.